Imagine standing at the edge of everything you have ever known, at the precipice of a darkness so absolute, so incomprehensibly vast, that even the concept of ending feels too small a word to contain it. Imagine looking up at the night sky, that ancient, familiar canvas of stars that human beings have gazed upon since the very first eyes opened on this world, and knowing, truly knowing in the deepest marrow of your bones, that every single point of light you see is already dying. That the universe itself, this magnificent, sprawling, impossibly beautiful cosmic cathedral that birthed galaxies and nebulae and black holes and life itself, is running down like a clock that was wound only once, billions of years ago, and has been ticking towards silence ever since. How does that make you feel? Sit with that question for a moment, because what you are about to hear is not science fiction. It is not mythology. It is not the fevered imagination of doomsday prophets. What you are about to hear is the story the universe is already telling, written in the language of physics, in the expansion of space-time itself, in the dying light of distant suns. And it is, without question, the most terrifying and the most magnificent story ever told. We are going to travel together through the most apocalyptic scenarios that the cosmos has to offer. Not the small apocalypses that human civilization fears, the wars, the pandemics, the asteroid strikes that might wipe out a single species on a single pale blue dot. No. We are going to go much, much further than that. We are going to explore the ends of worlds, the deaths of stars, the consumption of entire galaxies, and the ultimate fate of the universe itself. We are going to peer into scenarios so extreme, so mind-bending, so cosmically violent, that they make every human catastrophe in all of recorded history look like a gentle summer rain. And here is the most extraordinary thing. These scenarios are real. They are supported by the best science humanity has ever produced, confirmed by observations from the most powerful telescopes ever built, and calculated by some of the most brilliant minds our species has ever generated. The cosmos is not a peaceful, eternal backdrop to human drama. It is an arena of almost incomprehensible violence, operating on scales of time and space that shatter every human intuition we possess. Ask yourself this: what would it feel like to watch the sun go dark? Not slowly, not quietly, not in some abstract future so distant it feels meaningless, but to truly comprehend that day, to stand in its shadow, to understand what comes next. And then ask yourself, what comes after the sun? What comes after the stars? What comes after everything? Let us begin at the beginning. Not the beginning of time, we will get there, but the beginning of our journey through cosmic catastrophe. Let us start with something close to home, something that, on the scale of cosmic time, is almost disturbingly nearby. Let us start with the fate of our own solar system, because it is the most personal apocalypse we can conceive of, and because understanding it will prepare us for the horrors and wonders that lie beyond. The sun is, by almost any measure, an extraordinarily ordinary star. It sits in the outer arm of a spiral galaxy called the Milky Way, one of somewhere between 200 billion and 2 trillion galaxies in the observable universe. It is a middle-aged, medium-sized, yellow dwarf star, the kind of star that astronomers sometimes call a G-type main sequence star, which sounds clinical and cold but which conceals a truth of almost supernatural violence. Every single second, the sun converts approximately 600 million metric tons of hydrogen into helium through the process of nuclear fusion at its core. Every second. The energy released by that process, energy that takes anywhere from 10,000 to 100,000 years to fight its way from the core to the surface, is what we feel as sunlight on our faces, what drives the weather, what powers the photosynthesis that feeds every living thing on Earth. The sun is, in every meaningful sense, the engine of life as we know it. But engines run out of fuel. The sun has been burning for approximately 4.6 billion years. It has enough hydrogen fuel remaining in its core to continue burning for roughly another 5 billion years. In cosmic terms, our sun is middle-aged, sitting comfortably in the stable, hydrogen-fusing phase of its life that astronomers call the main sequence. But here is where the story turns dark, and here is where we should pay very close attention, because the end of the sun's main sequence life does not arrive quietly. As the sun exhausts the hydrogen at its core over the next several billion years, the nuclear reactions will begin to fail to balance the crushing inward pressure of gravity. The core will begin to contract and heat up. The outer layers of the sun, paradoxically, will begin to expand, and they will expand dramatically. Over a period of roughly 1 to 2 billion years, as the sun enters what astronomers call the subgiant phase and then the red giant phase, its outer atmosphere will swell to an almost incomprehensible size. The sun will grow to somewhere between 100 and 200 times its current diameter. Models suggest it will eventually engulf the orbits of Mercury and Venus entirely. And Earth. This is where the debate among astronomers becomes genuinely fascinating and genuinely terrifying. For decades, the consensus was that Earth would just barely escape being swallowed by the expanding sun, scorched to a cinder but not physically consumed. But research published in the early 21st century by astronomers, including Klaus-Peter Schroeder and Robert Conan Smith, published in the monthly notices of the Royal Astronomical Society, revised that picture considerably. Their calculations suggest that as the sun expands, the interactions between its expanding outer atmosphere and Earth's orbit, a process involving tidal forces and mass loss, may cause Earth to spiral inward, drawn toward the sun even as the sun expands toward Earth. The conclusion of their modeling was stark. Earth will most likely be engulfed and vaporized inside the sun's outer atmosphere. Think about that. The ground you stand on. Every mountain, every ocean, every city, every grave of every human who ever lived, consumed, turned to plasma, folded into the expanding belly of a dying star. Now, of course, this is 5 billion years away. No human civilization remotely resembling ours will exist to witness it. But the principle matters enormously because it tells us something fundamental about the nature of the cosmos. Nothing lasts. Not even the stars that give us life. But the expanding red giant phase, as catastrophic as it sounds, is only the beginning of the sun's death process. After the red giant phase, the sun will shed its outer layers in a glowing cloud of gas and dust called a planetary nebula, a misnomer coined in the 18th century because such objects resembled planets through early telescopes, when in fact they have nothing to do with planets. This glowing shroud of expelled gas, illuminated by the intensely hot stellar remnant at its center, will be visible across enormous distances of space, a ghostly ring or bubble of light drifting through the galaxy. And at the center of this nebula will be what remains of the sun's core, a white dwarf. A white dwarf is one of the most extraordinary objects in the known universe. It is approximately the mass of the sun compressed into a sphere roughly the size of Earth, so dense that a teaspoon of its material would weigh approximately 15 tons here on Earth's surface. The white dwarf that remains after the sun's death will be composed mostly of carbon and oxygen, the ash of the nuclear reactions that once powered the sun. It will be extraordinarily hot initially, surface temperatures of tens of thousands of degrees, but it will have no internal energy source. It will simply radiate its heat into space, cooling slowly over billions and billions of years, like an ember pulled from a fire and left in an empty room. Over timescales almost beyond comprehension, trillions of years, hundreds of trillions of years, a white dwarf will cool enough to become what theorists call a black dwarf, a cold, dark, inert remnant of a star, glowing with no more light than the background of space. But here is a fact that should genuinely stop you in your tracks. The universe is not yet old enough to contain a single black dwarf. The oldest white dwarfs we have observed are still warm enough to glow faintly. The universe at roughly 13.8 billion years old is simply too young for any star to have completed this entire journey to cold silence. Every black dwarf that will ever exist has not yet been born. We are, in cosmic terms, still in the early chapters of the story. Now let us zoom out. Let us leave our solar system behind, already a scorched, dark, sterile system orbiting a white dwarf, and look at what is happening on the scale of galaxies. Because the cosmos has apocalyptic scenarios that operate not on the scale of single stars, but on the scale of entire galactic empires containing hundreds of billions of stars. Our galaxy, the Milky Way, is a barred spiral galaxy containing somewhere between 100 billion and 400 billion stars. It is approximately 100,000 light-years in diameter. It is enormous by any human standard, and it is hurtling toward a collision. The Andromeda Galaxy, also known as Messier 31, our nearest large galactic neighbor, is currently approximately 2.5 million light-years away from us. It is approaching the Milky Way at a speed of roughly 110 kilometers per second, that is 396,000 kilometers per hour, and in approximately 4.5 billion years, it will collide with our galaxy in one of the most dramatic events in the local universe. Astronomers have a name for the merged galaxy that will result. They call it Milkomeda, or sometimes Milkdromeda, and the collision they predict is supported by extraordinarily precise measurements from the Hubble Space Telescope, published by researchers including Roland van der Merel and his colleagues at the Space Telescope Science Institute. Now, you might imagine a collision between two galaxies as being like two ships ramming into each other. Catastrophic, violent, immediately and obviously destructive. But galaxy collisions are stranger and more uncanny than that, because of the extraordinary emptiness of galaxies themselves. The distances between individual stars within a galaxy are so vast that even when two galaxies collide and merge, the stars almost never physically crash into one another. Instead, what happens is a gravitational ballet of almost unimaginable complexity and beauty. The galaxies interpenetrate one another, their stars sweeping past each other at cosmic distances, the gravitational interactions throwing stars out of their orbits, drawing long tidal tails of stellar material out into intergalactic space, igniting enormous bursts of star formation as gas clouds are compressed together, and eventually, over a period of hundreds of millions to billions of years, settling into a merged elliptical galaxy. So is the collision of the Milky Way and Andromeda the end of the world? Not in the way you might think. The solar system, if it still exists in some form by then, has a small but non-zero chance of being ejected from the merged galaxy entirely, sent drifting into intergalactic space as a solitary system in the void between galaxies. But the collision itself is not the apocalypse. It is a transformation. And yet, and this is where the story deepens into something truly unsettling, the collision will dramatically reshape the conditions for star formation and stellar death throughout the merged system, and will be one of the most violent events in the history of our corner of the universe. Let us now talk about something that makes galaxy collisions look gentle by comparison. Let us talk about something that sits at the center of our own galaxy right now, something we know is there, something we have actually observed, and something that represents one of the most extreme environments in all of known physics. At the center of the Milky Way, approximately 26,000 light-years from Earth, there is a compact radio source called Sagittarius A star. For decades, astronomers suspected this was a supermassive black hole. Then came the observations. Using radio telescopes, infrared telescopes, and decades of painstaking data collection, astronomers tracked the orbits of individual stars near the galactic center and found them moving in ways that could only be explained by the gravitational influence of an extraordinarily massive object. An object with a mass of approximately 4 million times that of our Sun, compressed into a region smaller than our solar system. The Nobel Prize in Physics for 2020 was awarded in part to Reinhard Genzel and Andrea Ghez for their discovery of this supermassive compact object at the center of the Milky Way, confirming decades of observational evidence. And then, in April 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole. Not Sagittarius A star initially, but the supermassive black hole at the center of the galaxy Messier 87, a beast with a mass of 6.5 billion times that of our Sun, surrounded by a glowing accretion disk of superheated gas. The image showed what looked like a glowing orange ring with a dark central region, the shadow of the event horizon, the point of no return beyond which nothing, not even light, can escape. In 2022, the same collaboration released an image of Sagittarius A star itself, confirming its nature directly for the first time. We have, for the first time in human history, seen a black hole. But what does a supermassive black hole actually do to the universe around it? What are its apocalyptic capacities? Because a black hole sitting quietly at the center of a galaxy is one thing. A black hole that is actively feeding is something else entirely. Something that makes it one of the most destructive forces the cosmos has ever produced. When a supermassive black hole actively accretes, that is, When it is consuming large amounts of gas and dust and stars, it becomes what astronomers call an active galactic nucleus, and in its most extreme form, a quasar. Quasars are among the most luminous objects in the known universe. They can outshine entire galaxies containing hundreds of billions of stars. The most luminous quasar ever discovered, designated J0529-4351 and reported by astronomers in 2024, was found to be consuming the equivalent of one solar mass of material every single day, making it 700 trillion times more luminous than our Sun, the most luminous object ever discovered in the universe as of the time of that announcement. Think about what it means to consume an entire star's worth of mass every single day. The energy released by that process is not released quietly. It is ejected in enormous jets of plasma moving at nearly the speed of light, extending for hundreds of thousands of light years, longer than the diameter of the galaxy itself. These jets can heat and disperse the gas within a galaxy, essentially shutting down star formation across the entire galactic system. They can affect neighboring galaxies. They are, in the most literal possible sense, civilization-ending forces on a galactic scale. Any world existing within the range of a quasar jet would be bathed in radiation so intense that no chemistry complex enough to produce life could survive. And here's a question worth sitting with. We know that the Milky Way's central black hole, Sagittarius A star, was once active. Astronomers have found evidence of enormous bubbles of hot plasma extending tens of thousands of light years above and below the galactic plane. Structures called the Fermi bubbles, discovered by the Fermi Gamma-ray Space Telescope, that appear to be the remnants of past energetic activity at the galactic center, possibly from a period when Sagittarius A star was feeding actively. Our galaxy has already experienced something akin to a quasar episode. What would happen if it became active again? When the Milky Way and Andromeda merge, the collision will funnel enormous quantities of gas toward the galactic center, potentially reigniting both central black holes in a frenzy of accretion. The merged Milkomeda galaxy could, for a period of time, glow as a luminous active galactic nucleus, flooding the surrounding region of the universe with radiation. For any life that might exist in or near this merged system, it would be cataclysmic. And this is not speculation in the sense of being unsupported. This is the expected behavior of merging galaxies with central black holes, observed in hundreds of other galactic mergers across the universe. But we have not yet touched the scenarios that operate on truly cosmic scales. We have not yet talked about what happens not to individual stars or individual galaxies, but to the universe itself. Because the cosmos has its own death sentence, and it has been known to physicists for decades, and it is written into the fundamental laws of thermodynamics, laws that no force in the universe has ever been observed to violate. The second law of thermodynamics states that in any closed system, entropy, a measure of disorder of the dispersal of energy, always increases over time. Never decreases. Always increases. And the universe, as best we can tell, is effectively a closed system. That means that entropy in the universe has been increasing since the moment of the Big Bang, will continue to increase, and will continue to increase until it reaches its maximum possible value. A state of maximum disorder, maximum uniformity, maximum stillness, in a scenario that physicists call the heat death of the universe, or the Big Freeze. But before we arrive at the heat death, there are other cosmic apocalyptic scenarios that have been proposed by physicists, each more extraordinary and unsettling than the last. And the extraordinary thing is that which one is correct depends on details of physics that we do not yet fully understand. Details about the nature of dark energy, dark matter, and the ultimate fate of the quantum vacuum itself. We are going to explore each of these scenarios in depth, because each one tells us something profound and astonishing about the nature of existence itself. Let us start with dark energy, because without understanding dark energy, none of the truly ultimate cosmic catastrophes make any sense. Dark energy is, quite simply, one of the most mysterious and disturbing discoveries in the history of science. In 1998, two independent teams of astronomers, led by Saul Perlmutter on one side and by Brian Schmidt and Adam Rees on the other, were studying Type Ia supernovae, a type of stellar explosion that produces a known luminosity and can therefore be used as a standard candle to measure cosmic distances. They expected to find that the expansion of the universe, which had been underway since the Big Bang, was slowing down due to the gravitational attraction of matter. What they found instead shattered every expectation. The expansion of the universe was not slowing down. It was speeding up. The universe is accelerating in its expansion. Something is pushing space itself apart at an ever-increasing rate. Something that exists everywhere in space, in the vacuum itself, and that has a repulsive gravitational effect, the opposite of the gravitational attraction of matter. This something was named dark energy, and it remains, to this day, one of the most profound mysteries in all of science. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for 2011 for this discovery. We do not know what dark energy is. We have theories, the leading one being that it is a property of space itself, sometimes called the cosmological constant, a concept that Einstein actually introduced into his equations of general relativity and then famously called his greatest blunder, only for it to turn out to be correct after all. But we do not understand its physical origin. We do not understand why it has the precise value it has. And crucially, we do not know whether it is constant or whether it can change over time. That uncertainty is the key, because the fate of the universe, the ultimate cosmic apocalypse, the ending of all endings, depends critically on what dark energy does over cosmic time. And the different possibilities range from the merely terrifying to the genuinely incomprehensible. Let us begin with the scenario that most cosmologists currently consider most likely, based on available evidence, and which is the coldest and loneliest of all fates. The heat death of the universe, or as it is sometimes more poetically called, the Big Freeze. In this scenario, dark energy remains constant, or close enough to constant that the universe continues its accelerating expansion indefinitely. Galaxies that are not already gravitationally bound to each other will continue to recede from one another at ever-increasing speeds, eventually receding so fast that the light from them can never reach us. The observable universe, that sphere of space from which light has had time to reach us since the Big Bang, will shrink in terms of what we can see or communicate with. The rest of the universe, already out there, will become forever unreachable, effectively invisible, as the expansion carries it beyond our cosmic horizon. We are already in this process. The vast majority of the universe is already beyond our observable horizon and is receding from us faster than light. Not because anything is traveling faster than light through space, but because space itself is expanding between us and those distant regions. Star formation in galaxies will gradually slow as the available gas is either consumed by existing stars or heated and dispersed by stellar feedback and galactic winds. The last generation of stars will form. Not the brilliant, short-lived massive blue stars that burn for millions of years, but the smallest, dimmest, most miserly of stellar objects. Red dwarf stars, stars so small and cool and careful with their fuel that they can burn for 10 trillion to 100 trillion years. Red dwarf stars are the marathoners of the stellar world, the long-distance runners who will outlast every other type of star by extraordinary margins. The universe as we know it, with its galaxies, its star clusters, its nebulae, its planetary systems, is, in the long view, almost absurdly young and temporary. The era of bright, hot, short-lived stars is already beginning to wind down. The future belongs to the red dwarfs. But even the red dwarfs will eventually exhaust their fuel. And as they do, one by one, over timescales of 10 trillion years, they will cool and fade. Some will briefly swell into red giants before collapsing into white dwarfs. Others, the very smallest, will simply cool directly into dark stellar remnants. And as the last red dwarf fades, something extraordinary happens. The universe enters a new phase of existence, one that cosmologists call the degenerate era. This is an era in which the universe contains no burning stars, only white dwarfs, neutron stars, black holes, and the dead remnants of planets, drifting through a darkness so complete that there is no light source anywhere to illuminate it. The degenerate era will last for perhaps 10 to the power of 37 years, that is 10 followed by 37 zeros. A number so large that writing it out and reading it fails to convey its magnitude. For perspective, The current age of the universe is approximately 10 to the power of 10 years. The degenerate era will last for a period that makes the current age of the universe look like an eye blink at the beginning of a story whose final page is incomprehensibly distant. During the degenerate era, white dwarfs will slowly cool toward absolute zero, as we discussed, destined to become black dwarfs over timescales so immense that none will have yet completed that journey even by the end of the degenerate era. Neutron stars, the ultra-dense remnants of massive stellar explosions, will cool and fade as well. And something else will happen, something predicted by a certain branch of physics that we have not yet directly observed but have excellent theoretical reasons to believe. Proton decay. The proton is one of the fundamental constituents of atomic nuclei, and until the middle of the 20th century, it was believed to be perfectly stable, immortal, essentially. But theories that attempt to unify the fundamental forces of nature, grand unified theories, or GUTS, generally predict that protons are not perfectly stable. They predict that protons have a finite lifetime, that eventually, given enough time, a proton will spontaneously decay into lighter particles. The predicted lifetime varies by theory, but a commonly cited lower bound, based on experimental non-detection of proton decay, places it at more than 10 to the power of 34 years, which means that by around 10 to the power of 40 years, within the degenerate era, essentially all protons in the universe will have decayed. Every atom, every molecule, every white dwarf, every neutron star, every dead planet, every molecule that was once part of a living being, all of it will dissolve into a thin mist of electrons, positrons, neutrinos, and photons. The matter phase of the universe, everything we have ever touched or seen or studied or loved, will come to an end. If proton decay does not occur, if protons turn out to be genuinely stable, as some theories allow, then the white dwarfs and neutron stars of the degenerate era will persist for far longer. But even they are not safe from another extraordinary process: quantum tunneling. Over incredibly vast timescales, quantum mechanical tunneling can cause the carbon and oxygen nuclei inside white dwarfs to slowly fuse into heavier elements, and eventually, over timescales on the order of 10 to the power of 1,500 years, quantum tunneling could cause a white dwarf to collapse into the lowest energy state available, converting it into a sphere of iron, the most stable of all atomic nuclei, in a process called cold fusion or quantum nucleosynthesis. And if quantum tunneling can collapse white dwarfs to iron spheres, it can theoretically, over even longer timescales, cause those iron spheres to collapse further, converting them into neutron stars, and ultimately, through a process called quantum tunneling to black holes, converting even cold iron spheres into black holes. These timescales are so immense, 10 to the power of 10 followed by 76 zeros, that they essentially lie beyond the horizon of comprehensibility. But let us talk about black holes, because they deserve their own moment in this story. By the time all matter has either decayed or undergone quantum tunneling into other forms, the universe will be populated primarily by black holes. The collapsed remnants of massive stars, the supermassive black holes at the centers of dead galaxies, and perhaps smaller black holes formed through quantum processes. In this black hole era, which cosmologists date to roughly 10 to the power of 40 to 10 to the power of 100 years, black holes will be the dominant structures in a dark, cold, empty universe. But even black holes do not last forever. And the process by which they eventually end was discovered by one of the most extraordinary minds of the 20th century, in what is arguably one of the most remarkable theoretical achievements in the history of science. In 1974, the physicist Stephen Hawking, building on earlier work by Jacob Bekenstein on black hole thermodynamics, made an astonishing prediction. Black holes are not truly black. They radiate. Through a subtle quantum mechanical process that occurs at the event horizon, black holes slowly emit energy in what is now called Hawking radiation. The mechanism is genuinely mind-bending. In quantum mechanics, the vacuum of space is not truly empty but is filled with pairs of virtual particles that spontaneously appear and annihilate each other on timescales shorter than the Heisenberg uncertainty principle allows to be detected. At the event horizon of a black hole, occasionally one member of such a pair falls into the black hole while the other escapes, and the black hole loses a tiny, tiny amount of mass energy in the process. Over time, this means that black holes slowly evaporate. The rate of evaporation is extraordinarily slow for large black holes. A stellar mass black hole would take on the order of 10 to the power of 70 years to evaporate through Hawking radiation, and a supermassive black hole of 1 billion solar masses would take something like 10 to the power of 100 years. But the key point is that the evaporation is real. It happens, and given sufficient time, all black holes will eventually evaporate. And as a black hole shrinks, the process accelerates, until in its final moments a black hole releases its remaining mass energy in a burst of Hawking radiation, a flash of high-energy particles and photons that represents the final death of one of the universe's most extreme objects. We have not yet directly detected Hawking radiation. The signal from any real black hole is far too faint to be detected with current instruments, but the theoretical foundations of Hawking's argument are among the most solid in theoretical physics, built on the intersection of quantum mechanics, thermodynamics, and general relativity. Its existence is accepted by virtually all physicists who work in these areas. The detection of Hawking radiation experimentally remains one of the great uncompleted quests of physics. After the last black hole evaporates, somewhere around 10 to the power of 100 to 10 to the power of 130 years, what remains? This is the heat death of the universe in its most complete form. The universe will be populated by an unimaginably thin, cold, nearly uniform gas of photons, neutrinos, electrons, and positrons, at an almost zero temperature, spread across an expanding void of almost incomprehensible size. The photons will have been redshifted by the cosmic expansion to wavelengths longer than the current size of the observable universe. The temperature of the universe will be vanishingly close to, but theoretically never quite at, absolute zero, because the expansion of space continuously generates a tiny residual radiation field. There will be no structures, no gradients, no order, nothing that could be called an event, because events require a gradient of energy, a difference between one region and another, and entropy will have reached its maximum. This is the heat death. This is the final silence. Or is it? Because there are alternative scenarios, and some of them are considerably more dramatic and considerably more violent than the long, cold, entropic fade of the heat death. Let us explore them, because they represent some of the most extraordinary ideas in modern cosmology. The first alternative is the Big Rip. The Big Rip scenario was first seriously developed and published by Robert Caldwell, Mark Kamionkowski, and Nevin Weinberg in a paper in 2003, and it depends on the nature of dark energy. In the standard cosmological model, dark energy has what is called an equation of state parameter W equal to -1, meaning its energy density stays constant even as the universe expands. This is the cosmological constant model. But some theories of dark energy, called phantom energy theories, allow for a value of W less than -1. And if that is the case, the energy density of dark energy does not stay constant but actually increases as the universe expands. And if dark energy's density increases, then the repulsive force driving the cosmic expansion does not merely stay constant, it grows stronger and stronger over time. The consequences of this are staggering. In the Big Rip scenario, the accelerating expansion eventually becomes so extreme that the dark energy, or phantom energy, begins to tear apart not just the distances between galaxies, but the galaxies themselves. Then the solar systems within those galaxies. Then the planets. Then the atoms. In the final moments of the Big Rip, which would occur at a specific finite time in the future depending on the value of W, the force of expansion exceeds every other force in the universe. Gravity, electromagnetism, the strong nuclear force, even the forces holding atomic nuclei together. And the universe is literally torn apart at every scale simultaneously. Every structure, every particle, every quantum field is ripped apart by the expanding fabric of space-time itself. The timeline of the Big Rip, if it occurs, is dramatic and precisely calculable. According to Caldwell and colleagues' original estimates, using a representative value of W, the Big Rip would occur approximately 22 billion years from now. In the final billion years before the rip, galaxies would be torn apart. In the final months, our solar system would become unbound. In the final minutes, Earth would be disrupted. In the final fraction of a second, atoms would be torn apart, and space-time itself would rip at every point simultaneously. And then, nothing. Not even the space-time geometry that could carry the concept of nothing would remain coherent. The Big Rip is, in a certain sense, the most violent conceivable end to the universe. Not a slow fade into cold silence, but a sudden, simultaneous, violent dismemberment of every structure and every particle at every scale in the cosmos. Current observations do not conclusively rule out the Big Rip. The measured value of W is consistent with -1, consistent with a cosmological constant, but the error bars in our measurements are large enough to accommodate values less than -1. Determining whether the Big Rip is our ultimate fate requires measurements of dark energy's equation of state to a precision that is currently beyond our capabilities, though next-generation surveys and observatories aim to narrow these constraints considerably. Now let us talk about a scenario that is even more philosophically unsettling than the Big Rip. A scenario that does not merely end the universe, but ends it in a way that raises profound questions about the nature of reality itself. A scenario called the false vacuum, or more precisely, vacuum decay. To understand vacuum decay, you need to understand a concept from quantum field theory: the vacuum energy, or the state of minimum energy of the universe. In quantum field theory, every point in space is associated with quantum fields, the fundamental fields that give rise to all particles and forces. The vacuum, empty space, is the state of these fields when no particles are present, and it has a certain energy associated with it called the vacuum energy. Now, the question is whether the vacuum of our universe is in its true lowest energy state, its true vacuum, or whether it is in a higher energy state that appears stable but is not, a false vacuum, like a ball sitting in a shallow depression on the slope of a hill, appearing stable but with a lower energy state available if it can just get over the lip of the depression. Current theoretical calculations, based on measurements of the Higgs boson mass and the top quark mass made at the Large Hadron Collider, suggest that our universe may indeed be in a metastable false vacuum, a state that appears stable but is not the true lowest energy state available. This conclusion was highlighted in papers by physicists including Joseph Lukin and Maria Spiropoulou, and was widely discussed in the physics community following the discovery of the Higgs boson at CERN in 2012. If the universe is in a false vacuum, then quantum mechanics allows for the possibility, vanishingly unlikely at any given moment, but with a non-zero probability per unit time per unit volume, that a bubble of true vacuum could spontaneously nucleate somewhere in space. This bubble would have lower energy than the surrounding false vacuum, and it would immediately begin to expand. The edge of the bubble wall, would expand outward at the speed of light. Everything it encountered, every particle, every field, every atom, every galaxy, would be converted into true vacuum, a region with entirely different laws of physics than our own. Different values of the fundamental constants. Different properties of the quantum fields. A region where atoms as we know them cannot exist, where chemistry cannot occur, where life is impossible. And the bubble wall, approaching at the speed of light, would be completely and utterly undetectable. No signal, no warning, no preparation would be possible, because nothing can travel faster than the bubble wall. The first indication that the bubble exists would be the moment it reaches you. And that moment would be the last moment of anything you could experience. Vacuum decay would be the most perfect apocalypse conceivable. It would be instantaneous, universal, and utterly beyond any defense or warning. Every structure in the universe, galaxies, stars, planets, atoms, would be erased, not merely destroyed, but fundamentally altered at the level of the laws of physics themselves. The universe after vacuum decay would not merely be dead. It would be a different universe, operating under different physical laws, in which nothing resembling the structures and phenomena of our universe would exist. Is this likely? Physicists are genuinely uncertain. The probability of spontaneous vacuum decay depends on the exact values of the Higgs boson mass and the top quark mass, which are known only to a certain precision, and on physics beyond the standard model that we have not yet discovered. Current best estimates suggest that the lifetime of the false vacuum, if our universe is indeed metastable, is much longer than the current age of the universe, possibly much longer. But the uncertainty is real, and the scenario is physically plausible, which is what makes it so extraordinary. This is not the fevered imagination of a science fiction writer. This is a legitimate, mathematically rigorous scenario discussed in peer-reviewed physics journals by some of the most careful minds working in fundamental physics. There is something philosophically extraordinary about the concept of vacuum decay, something that goes beyond mere physical apocalypse. It suggests that the laws of physics themselves are not eternal and fixed, but contingent, that the particular physics we observe in our universe, the physics that makes atoms and molecules and chemistry and biology and consciousness possible, is not the only possible physics, and is perhaps not even the most stable possible physics. We exist, in this view, in a lucky bubble of false vacuum that happened to be hospitable to the emergence of complexity and life, and that bubble's end could come without warning at any moment, anywhere in the universe. But let us now shift to a scenario that operates not at the level of quantum field theory, but at the level of the large-scale geometry of the universe itself. Let us talk about the Big Crunch. The Big Crunch is in some ways the classical apocalyptic scenario of cosmology, dating back to the earliest discussions of the universe's fate in the mid-20th century. It arises in models where the total energy density of the universe, the sum of matter, radiation, and dark energy, is above a critical value, making the universe what cosmologists call closed, meaning that gravity will eventually overcome the expansion and cause the universe to recontract. In the Big Crunch scenario, the expansion of the universe reverses. Instead of accelerating outward, galaxies begin to decelerate, stop, and then begin to fall back together. The cosmic microwave background, the ancient light left over from the Big Bang, now cooled to just 2.7 degrees above absolute zero, would begin to blue shifted as the universe contracts, growing hotter and hotter. Stars and galaxies would be compressed together. The temperature of the universe would rise. Eventually, the night sky would be as bright as the surface of a star everywhere, then hotter. Then the stars themselves would be disrupted by the radiation field. Then the atomic nuclei. Then the protons and neutrons would dissolve into their constituent quarks and gluons. And then, at the singular endpoint of the Big Crunch, all the matter and energy in the universe would be compressed into a singularity, a point of infinite density and infinite temperature that mirrors, in reverse, the singularity from which the Big Bang began. Does the current evidence support the Big Crunch? Not strongly. The discovery of dark energy and the observation of the universe's accelerating expansion make a Big Crunch appear unlikely under standard cosmological models, because dark energy seems to be overwhelming gravity on large scales. But models are only as good as our understanding of the physics, and our understanding of dark energy remains incomplete. Some researchers have speculated about the possibility that dark energy could change its behavior over time, that it could weaken or reverse, eventually allowing gravity to win. The possibility cannot be definitively ruled out, and it remains an active area of theoretical investigation. Some physicists and cosmologists have proposed an extension of the Big Crunch idea called the Big Bounce. The idea that the universe does not simply collapse into a singularity and stop, but that the extreme conditions of the crunch somehow give rise to a new Big Bang, a bounce that begins a new cycle of expansion. This is the basis of cyclic cosmology, proposed in various forms by researchers including Paul Steinhardt and Neil Turok, and representing one of the more extraordinary and philosophically provocative ideas in modern cosmology. In cyclic models, our universe is not the first and will not be the last. It is one of an infinite series of universes, each emerging from the collapse of the previous one, expanding, cooling, developing structure and life, and eventually reversing or fading into a state that seeds the next cycle. The cyclic universe idea is not currently the dominant model in cosmology, and many cosmologists argue that it faces significant theoretical challenges. But it is a genuine scientific proposal, not mere philosophy, and it raises some of the most profound questions imaginable. If the universe is cyclic, does anything persist from one cycle to the next? Does information survive the bounce? Could there be any continuity of structure or pattern across cycles? And most haunting of all, is there any meaningful sense in which the universe, or universes, are conscious of themselves? We do not know the answers to these questions. They sit at the frontier where cosmology meets philosophy, where physics meets questions of meaning and existence. And that frontier is precisely where the most interesting ideas in science always live. Now let us turn to something that is not a scenario for the ultimate fate of the universe, but is instead a scenario for something that could happen at any moment, anywhere in the cosmos, to any world that has the misfortune of existing in the wrong place at the wrong time. Let us talk about gamma-ray bursts. Gamma-ray bursts are, by a significant margin, the most energetic explosive events in the known universe since the Big Bang. They are brief, lasting anywhere from milliseconds to several minutes. But in that brief time, they release more energy than our sun will emit over its entire 10 billion year lifetime. In a matter of seconds. Some gamma-ray bursts release as much energy as all the stars in the observable universe emit in that same period of time, combined. They are the most luminous events we have ever observed, and they are also one of the most poorly understood phenomena in astrophysics. We have known about gamma-ray bursts since the 1960s, when they were accidentally discovered by the Vela satellites. Military satellites launched by the United States to detect nuclear test explosions in violation of the Partial Nuclear Test Ban Treaty. The satellites did detect bursts of gamma rays, but not from anywhere on Earth. They were coming from deep space. The military kept the discovery classified for several years before releasing the data to the scientific community in 1973, and the field has been in a state of dramatic discovery ever since. Gamma-ray bursts appear to come in two main categories. Short-duration gamma-ray bursts, lasting less than about 2 seconds, are now understood to be produced by the merger of two ultra-dense objects, two neutron stars, or a neutron star and a black hole. These mergers are also extraordinarily important for another reason. They are the primary forge of heavy elements in the universe. In the violent collision and merger of two neutron stars, the physical conditions, extreme density, extreme temperature, enormous fluxes of neutrons, allow for the rapid neutron capture process called the R process, which produces heavy elements like gold, platinum, uranium, and a large fraction of all elements heavier than iron. The gold in your wedding ring, the platinum in your jewelry, the uranium in nuclear reactors. Much of it was forged in the collision of neutron stars billions of years ago. This was directly confirmed in 2017 when the detection of gravitational waves from a neutron star merger, designated GW170817, observed by the LIGO and Virgo gravitational wave detectors, was followed by the observation of a short gamma-ray burst and a kilonova, a glowing fireball of freshly synthesized heavy elements expanding outward from the merger site. Long-duration gamma-ray bursts, lasting more than 2 seconds and sometimes for several minutes, are now understood to be produced by a different mechanism. The core collapse of extremely massive, rapidly rotating stars, a type of stellar death called a collapsar, or sometimes a hypernova. When the core of such a star collapses to form a black hole, the rapidly spinning material around it forms an accretion disk that powers two relativistic jets of matter and energy along the rotation axis, punching through the collapsing star and producing the gamma-ray bursts that we observe. The jets of a gamma-ray burst are tightly focused. They are not spherical explosions but narrow beams of radiation, which is why we only detect gamma-ray bursts when one of the jets happens to be pointed toward us. This also means that the true rates of gamma-ray bursts in the universe are much higher than the detected rates. We see only those whose jets are aimed in our direction. Correcting for this beaming factor, the true rate of long gamma-ray bursts in a galaxy like the Milky Way is estimated at perhaps 1 every few 100,000 to 1 million years. And now comes the truly terrifying question. What would happen to Earth if a gamma-ray burst went off within our galaxy and one of its jets happened to be pointed toward us? The answer is deeply unsettling. The primary danger from a nearby gamma-ray burst is not the direct radiation, though that would be lethal at very close range, but the effect on Earth's atmosphere. The intense gamma-ray and X-ray radiation from a gamma-ray burst would dissociate nitrogen molecules in the upper atmosphere, producing nitrogen oxides that would then catalytically destroy the ozone layer on a global scale. A gamma-ray burst within a few thousand light-years of Earth, close on galactic scales, could destroy enough ozone to expose the surface to lethal levels of ultraviolet radiation from the sun for months to years. The consequences would include massive die-offs of photosynthetic organisms, disruption of food chains, and potentially a mass extinction event. Some researchers have proposed that a gamma-ray burst may have been responsible for one of Earth's mass extinctions. The Ordovician-Silurian extinction event, approximately 443 million years ago, wiped out an estimated 85% of marine species. It is characterized by patterns in the fossil record that some scientists, including Audrey Malott of the University of Kansas and Brian Thomas, have argued are consistent with the effects of a nearby gamma-ray burst. Specifically, evidence for widespread depletion of ozone and increased UV radiation exposure, preserved in the patterns of extinction and survival across different marine groups. This remains a hypothesis, not a confirmed cause, and other researchers point to glaciation and sea level changes as the primary drivers of the Ordovician extinction. But the gamma-ray burst hypothesis is taken seriously enough to be published and debated in peer-reviewed journals. The good news, to the extent there's good news, is that long gamma-ray bursts appear to be associated with massive, rapidly rotating stars in low metallicity environments. That is, environments where the gas has not been enriched with heavy elements by previous generations of stars. The Milky Way today has relatively high metallicity, especially in its inner regions, which may reduce the rate of long gamma-ray bursts in our vicinity. Additionally, the probability of a burst being aimed precisely at Earth from within our galaxy is relatively low. But the probability is not zero, and given cosmic timescales of hundreds of millions of years, even low probabilities become significant. Let us now turn to a different kind of stellar catastrophe, one that is not distant and directional but instead involves one of the most extraordinary objects in our own cosmic neighborhood. Let us talk about magnetars. A magnetar is a type of neutron star, the ultra-dense remnant formed when a massive star undergoes a core-collapse supernova. Neutron stars themselves are extraordinary. They pack between 1 and 2 solar masses into a sphere roughly 20 kilometers across, making them so dense that a tablespoon of neutron star material would weigh approximately 1 billion tons on Earth. The gravity at the surface of a neutron star is somewhere around 200 billion times the gravity at Earth's surface. They rotate rapidly, sometimes hundreds of times per second, and they generate powerful magnetic fields. But magnetars take this to an entirely different level. A magnetar is a neutron star with a magnetic field of extraordinary strength, on the order of 10 to the power of 15 Gauss, which is roughly 1 quadrillion times stronger than Earth's magnetic field and roughly 1,000 times stronger than the typical magnetic field of an ordinary neutron star. These fields are so strong that they distort the structure of atoms themselves. In a magnetic field this strong, atoms are stretched into cigar shapes along the field lines because the electrons' orbits are deformed by the magnetic force. The concept of a hydrogen atom as we know it, a proton orbited by an electron in a spherical probability cloud, would not exist in the vicinity of a magnetar. Physics as we know it simply breaks down at these field strengths. Magnetars are extraordinarily active objects. They periodically release enormous bursts of X-rays and gamma rays through a process related to the catastrophic restructuring of their magnetic fields. Processes called starquakes and flares. These events can release, in fractions of a second, more energy than our Sun emits in 100,000 years. On December 27, 2004, Earth was struck by a burst of radiation from a magnetar called SGR 1806-20, located approximately 50,000 light-years away. Despite being 50,000 light-years distant, this single event, which lasted about 0.2 of a second, was so energetic that it briefly saturated and disrupted gamma-ray detectors in Earth orbit, ionized the upper atmosphere, and was detectable even on the opposite side of Earth from the source because the radiation penetrated the planet. Astronomers estimated that it was the most intensely bright event detected from beyond our solar system since the supernova of 1987. If SGR 1806-20 had been located within a few light-years of Earth rather than 50,000, the burst would have been catastrophic, energetic enough to strip away the ozone layer and expose the surface to lethal radiation. We were, in a sense, extraordinarily lucky. The universe, as we are beginning to see, is a place where extraordinary violence routinely occurs at distances that make the difference between a detected scientific event and a mass extinction. Now let us move to something that combines the violence of stellar death with a scale so immense it challenges the imagination. Supernovae. We have mentioned supernovae in passing, but they deserve their own moment of attention, because they are the primary mechanism by which the chemical complexity of the universe is built and distributed, and they are also among the most violent individual events the cosmos can produce. When a star with a mass of roughly 8 to 100 solar masses reaches the end of its nuclear burning life, when it has exhausted its hydrogen, then helium, then carbon, neon, oxygen, and silicon in successive layers, building up an iron core, it faces a crisis. Iron is the most stable nucleus in nature. It cannot release energy by fusing into heavier elements, and it cannot release energy by fissioning into lighter elements. When the iron core grows to approximately 1.4 solar masses, a value called the Chandrasekhar limit, derived by the Indian-American astrophysicist Subramanian Chandrasekhar in the 1930s, it is no longer supported against gravitational collapse by electron degeneracy pressure. The core collapses. In less than a second, the outer iron core falls inward at roughly 1/4 the speed of light. The inner core reaches nuclear density, the density of atomic nuclei, and rebounds, sending a shock wave outward through the infalling material. This shock wave, possibly aided by an enormous flux of neutrinos generated by the collapsing core. Neutrinos so abundant that even though they interact extremely weakly with matter, the dense infalling envelope absorbs enough of them to deposit enormous energy, blows the star apart. The result is a core collapse supernova, one of the most energetic events in the universe. The energy released by a core collapse supernova is approximately 10 to the power of 44 joules. To put that in perspective, our Sun will emit approximately 4 times 10 to the power of 26 joules per second over its entire lifetime, and a supernova releases 100 times more energy than the Sun will emit over 10 billion years, in a matter of seconds. And the vast majority of this energy, about 99% of it, is not released as visible light, X-rays, or gamma rays, but as neutrinos. The supernova shines for weeks in the electromagnetic spectrum at a luminosity that can rival an entire galaxy containing hundreds of billions of stars, and yet even this extraordinary display represents only about 1% of the total energy released. The heavy elements forged in the nuclear fires of the dying star and in the ejecta of the explosion, carbon, oxygen, silicon, sulfur, iron, and many others, are distributed into the surrounding space, where they enrich the interstellar medium and eventually become part of new generations of stars and planets. We are, in the most direct and literal sense, made of stardust, specifically of the nuclear ashes of stars that exploded billions of years ago before the solar system formed. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it was forged in the nuclear reactions of stars and distributed into space by supernova explosions. The universe built you through a process that involved billions of years and the deaths of countless stars. But supernovae are not merely the factories of elements. They are also potential death machines for any civilizations unlucky enough to be nearby. The effects of a supernova depend strongly on distance. At distances of several tens of parsecs, roughly 100 light-years, a nearby supernova could expose Earth to lethal doses of cosmic rays and hard radiation, disrupting the ozone layer and causing significant damage to complex life. Some researchers have proposed that a nearby supernova may have contributed to the late Devonian mass extinction approximately 375 million years ago, though this remains controversial. The geological record does preserve evidence of elevated cosmic ray fluxes and related biological stress during certain extinction events, but establishing a direct causal link to a supernova is challenging. What about supernovae within 10 light-years of Earth? What would happen then? The answer is that the outcome would be almost certainly fatal for life on Earth's surface. At that distance, the flux of X-rays, gamma rays, cosmic rays, and high-energy particles would be sufficient to essentially strip away the ozone layer, severely damage or kill photosynthetic organisms, and expose the surface to radiation levels incompatible with the survival of complex multicellular life. Fortunately, the stellar density in the solar neighborhood is low enough, and the rate of supernovae in the Milky Way is low enough, roughly one every 50 years on average, and predominantly in the dense inner regions of the galaxy far from Earth, that the probability of a sufficiently close supernova in the next million years is small. But again, not zero. And here is a remarkable fact. We have a supernova candidate visible in our night sky with the naked eye, and it has been making news in recent years. Betelgeuse, the red supergiant star in the constellation Orion, located approximately 700 light-years from Earth, is a star in the late stages of its life. It is a red supergiant with a mass of roughly 15 to 20 solar masses. Precisely the type of star expected to undergo a core collapse supernova. In late 2019 and early 2020, Betelgeuse dimmed dramatically and unexpectedly, an event that became known as the Great Dimming, sparking enormous public interest and speculation that it might be on the verge of exploding. Subsequent analysis determined that the dimming was caused by a combination of a large ejection of material from the star's surface that condensed into dust, temporarily blocking our view of parts of the star's surface, and a coincident cool spot on the star's surface. Betelgeuse has since returned to normal brightness and has shown further variability. When Betelgeuse does explode, which could happen tomorrow, or in 100,000 years, or somewhere in between, given astronomers' estimates, it will be a spectacular event visible from Earth. It will be bright enough to cast shadows at night, visible in daylight, and will be one of the most dramatic astronomical events in human history. At 700 light-years, it will be completely safe from Earth, far too distant to pose any threat whatsoever to our biosphere. But it will serve as a spectacular reminder that the universe's violent processes are ongoing, that stellar death is not just a concept from the distant past or the far future, but something that is happening right now, right in our cosmic neighborhood. Now, let us explore a category of cosmic catastrophe that sits at the intersection of the astronomical and the terrestrial: asteroid and comet impacts. Because while these events are, by cosmic standards, almost trivially small, events local to a single planetary system, affecting a single world, they represent the most likely mechanism by which cosmic violence could directly intersect with human civilization on timescales of millions of years or less. And they have already shaped the history of life on Earth in ways both dramatic and profound. The most famous impact in Earth's history occurred approximately 66 million years ago. The Chicxulub impact, named after the town of Chicxulub in Mexico's Yucatan Peninsula, near the center of the roughly 180-kilometer diameter impact crater. The object that struck was an asteroid or comet estimated to have been approximately 10 to 15 kilometers in diameter, a boulder the size of a city, moving at approximately 20 kilometers per second. The energy released by the impact is estimated at roughly 10 billion times the energy of the nuclear bomb that destroyed Hiroshima. The impact excavated a crater, sent material into space, ignited global wildfires, produced enormous tsunami waves, and most significantly, ejected so much dust and sulfur dioxide into the stratosphere that it blocked sunlight for months to years, causing a global winter that collapsed photosynthesis and devastated food chains worldwide. The result was the end Cretaceous mass extinction, the most famous mass extinction in the fossil record, the one that ended the reign of the non-avian dinosaurs and approximately 75% of all species on Earth. It also, incidentally, cleared the ecological stage for the rapid diversification of mammals that eventually produced us. We exist, in a real sense, because of a cosmic accident 66 million years ago. An asteroid eliminated our competition and opened the niches that our mammalian ancestors evolved to fill. The evidence for the Chicxulub impact as the cause of the end Cretaceous extinction is overwhelming. The discovery of the worldwide iridium anomaly at the Cretaceous-Paleogene boundary, iridium being rare on Earth's surface but abundant in asteroids, by Walter and Luis Alvarez and colleagues in 1980, the subsequent discovery of the Chicxulub crater itself, the presence of shocked quartz and glass spherules at the boundary in countless geological sections worldwide, and the precise timing of the extinction with the impact event, confirmed by radiometric dating to extraordinary precision. Could this happen again? Of course it can. The solar system contains an enormous number of asteroids. Hundreds of thousands of near-Earth objects have been catalogued. And while the rate of truly massive impacts like Chicxulub is very low, perhaps once per 100 million years or so for impactors in the 10-kilometer range, it is not zero. There are also comets from the Oort cloud, a vast, distant reservoir of icy bodies surrounding the solar system at distances of up to 100,000 astronomical units, that can be perturbed by gravitational interactions and sent on trajectories that bring them into the inner solar system on timescales of months, making detection and deflection challenging. Human civilization has, for the first time in Earth's history, developed the capacity to detect incoming asteroids and potentially deflect them. The Planetary Defense Program at NASA, the European Space Agency, and other space agencies around the world has made significant progress in cataloging near-Earth objects. And in September 2022, NASA's DART mission, the Double Asteroid Redirection Test, successfully altered the orbit of the small moonlet Dimorphos by crashing a spacecraft into it at high speed, demonstrating for the first time that humanity has the technology and principle to deflect an asteroid. The mission was a genuine triumph of planetary defense, and it changed Dimorphos's orbital period by approximately 33 minutes, far more than the minimum required to classify the mission as a success. But there are categories of cosmic catastrophe that even our best planetary defenses cannot address. What about a rogue star passing close to our solar system? Over billions of years, the random motions of stars in the galaxy can occasionally bring stars within a few light-years of our solar system, close enough to gravitationally perturb the Oort cloud and send a shower of comets into the inner solar system. This is thought to happen on timescales of millions to tens of millions of years, and may be related to periods of elevated impact rates on Earth that some researchers have correlated with biological extinction events. The probability of a star passing close enough to directly destabilize planetary orbits is much lower, but not zero over geological timescales. What about the possibility of a nearby neutron star or stellar remnant that has not yet been detected? The nearest known neutron star is RxJ 1856.5-3754, at a distance of approximately 400 light-years, perfectly safe. But the detection of neutron stars is challenging. They are small and often dark, detectable only if they emit radio pulses or X-rays. Is it possible that an undetected neutron star is lurking within a few dozen light-years of our solar system? This is extremely unlikely given the completeness of nearby stellar surveys, but it is the kind of question that keeps astronomers cataloging the sky with increasing thoroughness. Now let us step back and consider something that is not a physical mechanism of destruction, but a conceptual framework that frames all of these scenarios in a new and unsettling light. Let us talk about the Fermi paradox, the strange and haunting silence of the cosmos. In 1950, the physicist Enrico Fermi, during a casual lunchtime conversation at Los Alamos National Laboratory, asked a question that has haunted scientists ever since. Where is everybody? The universe is approximately 13.8 billion years old. It contains hundreds of billions of galaxies, each containing hundreds of billions of stars. Many of those stars have planets. A significant fraction of those planets may be capable of supporting life. Given these numbers, and given that even a civilization modestly more advanced than ours could in principle spread across an entire galaxy in tens of millions of years, a blink in cosmic time, where are the signs of other civilizations? Where are the radio signals, the megastructures, the interstellar visitors? The universe appears strangely, deeply, unsettlingly empty of other intelligent life. This observation has been formalized as the Fermi paradox, and it has produced a rich and disturbing body of literature attempting to explain the silence. The explanations range from the optimistic, perhaps intelligent life is simply rare, or interstellar travel is more difficult than we think, or advanced civilizations signal in ways we haven't thought to look for, to the deeply disturbing. And it is the disturbing explanations that concern us here, because many of them invoke the very cosmic catastrophes we have been discussing. One of the most chilling proposed resolutions to the Fermi paradox is the concept of the Great Filter, proposed by economist Robin Hanson in 1998 and discussed and expanded by philosophers and scientists including Nick Bostrom. The Great Filter is some step in the development from simple matter to complex technological civilization that is extraordinarily unlikely, so unlikely that it explains why the universe appears to contain no other civilizations. The terrifying question is, where in the developmental sequence does the Great Filter lie? If the Great Filter is behind us, if the extraordinarily improbable step was something in our past, perhaps the emergence of eukaryotic cells, or multicellular life or intelligence, then we may be alone or nearly alone in the universe, which is lonely but survivable. But if the great filter is ahead of us, if there is something that destroys virtually every technological civilization before it can spread through the cosmos, then the silence of the universe becomes a warning. And that warning may be related to the cosmic catastrophes we have been discussing: nearby supernovae, gamma-ray bursts, asteroid impacts, the instability of planetary climates, or something we have not yet imagined. Nick Bostrom has written that the discovery of even simple life elsewhere in the universe, on Mars, on one of Jupiter's moons, would be one of the most terrifying discoveries in human history, because it would imply that the great filter is not in our past but possibly ahead of us. The more life we discover elsewhere, the more it implies that getting to complex life is not the difficult step, which means the filter must be elsewhere, and must be something that kills civilizations rather than prevents their emergence. The argument is counterintuitive and deeply unsettling, and it is one of the more remarkable contributions of philosophy to our understanding of cosmic risk. But let us now turn to a subject that is perhaps the most mind-expanding and the most recently developed of all the cosmic catastrophe scenarios: the possibility that our universe is not alone, the possibility of a multiverse, and the catastrophic implications that come with it. The idea of a multiverse is not, despite its appearance in science fiction, merely a speculative fantasy. It emerges naturally from some of the most well-developed and well-tested theories in modern physics. In inflationary cosmology, the theory that the universe underwent an extraordinarily rapid exponential expansion in its first tiny fraction of a second after the Big Bang, originally proposed by Alan Guth in 1980 and developed by Andre Linde, Paul Steinhardt, and others, quantum fluctuations during the inflationary period can produce a situation called eternal inflation, in which inflation never truly ends everywhere at once. Instead, different regions of the inflating space stop inflating at different times, each forming a separate, disconnected universe, a bubble universe, with potentially different physical laws, different values of the fundamental constants, and different physical properties. Our observable universe would be one such bubble, surrounded by an infinite sea of other bubble universes with which we can never interact, because the inflationary spacetime between them expands faster than light. In this eternal inflation picture, the multiverse is not a single universe but an infinite collection of universes, and the values of physical parameters within each universe, things like the strength of gravity, the mass of the electron, the value of the cosmological constant, are determined by the details of how inflation ended in that particular bubble. Different bubbles, different physics. In most bubbles, the physics would be hostile to the formation of complex structures. The cosmological constant might be so large that space expands too fast for galaxies to form, or gravity might be too weak for stars to form, or the value of certain parameters might prevent the formation of stable atoms. Only in a small fraction of bubbles would the physics be fine-tuned enough to allow complexity, chemistry, and life. This is sometimes invoked as an explanation for the anthropic coincidences, the seemingly miraculous fine-tuning of the physical constants for life, without requiring a designer. There is no fine-tuning, just selection. We exist in a bubble where the physics allows for life because that is the only kind of bubble we could observe. What are the catastrophic implications of the multiverse for our universe? One involves the false vacuum scenario we discussed earlier. In eternal inflation, the quantum tunneling that could produce vacuum decay, the nucleation of a bubble of true vacuum, could be seeded by the boundary conditions between different bubble universes. A collision between our bubble and a neighboring bubble universe would be a catastrophic event, potentially disrupting the physics of the region near the collision boundary. Remarkably, some physicists have argued that such a collision might leave observable signatures in the cosmic microwave background, patterns of temperature or polarization anomalies that deviate from the expected statistical distribution. Some anomalies in the CMB have been noted and discussed in this context, including a large cold spot observed by the WMAP and Planck satellites, though most cosmologists currently attribute such features to statistical fluctuation rather than bubble collision. The search for such signatures is active and ongoing. The multiverse raises another deeply unsettling possibility: the simulation hypothesis. This is technically a hypothesis about the nature of consciousness and computation rather than about physics per se, but it has been articulated most influentially by philosopher Nick Bostrom and has been discussed seriously by physicists including Max Tegmark and by technology entrepreneurs including Elon Musk. The simulation hypothesis asks, if a sufficiently advanced civilization can create computer simulations of universes that are indistinguishable from real universes to the beings within them, and if such civilizations eventually do create many such simulations, then by simple counting arguments, the probability that we are in one of the simulated universes is much higher than the probability that we are in the single real one. And if we are in a simulation, then the ultimate cosmic catastrophe is not a physical process at all, but the termination of the simulation, a shutdown that would be, from within the simulation, indistinguishable from the universe simply ceasing to exist everywhere instantly. This is not physics in the traditional sense. There is no equation that tells us how to distinguish a simulated universe from a real one, and many physicists argue the hypothesis is not scientifically testable. But it is a logical argument based on premises that are difficult to simply dismiss, and it has the interesting property of providing another category of great filter, one that could terminate technological civilizations not through physical catastrophe but through the decision of their simulators. Let us now return to firm physical ground and explore one of the most extraordinary and recently confirmed predictions of Einstein's general theory of relativity: gravitational waves. Because gravitational waves are not merely a new way of observing the cosmos. They open a window onto events so violent and energetic that they genuinely defy comprehension. Einstein predicted the existence of gravitational waves in 1916 as a consequence of general relativity. When massive objects accelerate, particularly when they spiral together and merge, they create ripples in the fabric of space-time itself, analogous to the ripples produced when a stone is dropped into a still pond. These ripples propagate outward at the speed of light, carrying energy and information about the event that produced them. Despite their extraordinary astrophysical violence, gravitational waves interact so weakly with matter that they pass through everything: planets, stars, galaxies, with essentially no attenuation. By the time a gravitational wave from even an extremely energetic event reaches Earth, it produces a stretching and squeezing of spacetime by a fractional amount of around 1,000th the diameter of a proton. Detecting such a signal is one of the most extraordinary feats of precision engineering in human history. On September 14, 2015, the Advanced LIGO Gravitational Wave Detectors, facilities in Hanford, Washington, and Livingston, Louisiana, detected the first gravitational wave signal ever recorded. The signal, designated GW150914, was produced by the merger of two black holes with masses of approximately 36 and 29 times the mass of the Sun, located approximately 1.3 billion light-years away. In less than a second of merger, the system emitted more power in gravitational waves than all the stars in the observable universe emit in electromagnetic radiation. About 3 solar masses of energy converted to gravitational wave energy in a fraction of a second. The signal that reached Earth moved the LIGO mirrors by an amount roughly 1,000th the diameter of a proton, and the detector caught it. Kip Thorne, Barry Barish, and Rainer Weiss received the Nobel Prize in Physics in 2017 for their roles in this achievement. Since then, the LIGO, Virgo, and CAGRA gravitational wave detector network has detected dozens of gravitational wave events, black hole mergers, neutron-star mergers, and possibly black hole neutron-star mergers, opening a completely new observational window on the most violent events in the universe. Each detection is a message from an event of almost incomprehensible violence, transmitted across billions of light-years, decoded by the extraordinary sensitivity of human-built instruments. But there is a class of gravitational wave source even more extraordinary than individual binary mergers: the gravitational wave background. Just as the cosmic microwave background is a relic of the Big Bang itself, the thermal radiation left over from the early universe, cosmologists predict the existence of a stochastic gravitational wave background, a superposition of gravitational waves from all sources across the universe, including merging black holes, merging neutron stars, and potentially gravitational waves produced during the inflationary epoch itself. Detecting this background would open a window on the very first moments of the universe's history. Moments that are completely opaque to electromagnetic radiation, because the early universe was so hot and dense that photons could not travel freely. In 2023, for major pulsar timing array collaborations, the North American Nanohertz Observatory for Gravitational Waves, the European Pulsar Timing Array, the Indian Pulsar Timing Array, and the Chinese Pulsar Timing Array announced simultaneously that they had detected strong evidence for a gravitational wave background using pulsar timing arrays, networks of rapidly rotating neutron stars used as extraordinarily precise natural clocks. The signal observed is consistent with the expected background from supermassive black hole mergers across the universe, and possibly contains contributions from more exotic sources. It was announced as strong evidence, not yet definitive detection, but a major step, and represented one of the most significant developments in observational astrophysics of the early 21st century. The future of gravitational wave astronomy includes planned space-based detectors, particularly LISA, the Laser Interferometer Space Antenna, a European Space Agency mission planned for launch in the 2030s, that will be sensitive to gravitational waves at lower frequencies than the ground-based detectors, allowing the detection of signals from supermassive black hole mergers, the gradual spiral of stellar mass objects into supermassive black holes, and potentially from the very early universe. LISA will extend gravitational wave astronomy to cosmological scales and will provide a new way of probing the most extreme environments the universe has to offer. Now let us turn to something that sits not in the distant future or the distant past, but very much in the present. Something that is happening right now, in our lifetimes, on Earth, and that connects the cosmic and the terrestrial in ways that have profound implications for the long-term fate of life on this planet. Let us talk about the current situation of Earth itself within the context of cosmic time and cosmic risk, and what it tells us about the conditions for life in the universe. Earth is, by any measure, an extraordinarily fortunate planet. Its distance from the Sun places it within the habitable zone, the range of distances where liquid water can exist on a planetary surface under standard conditions. It has a large moon, formed in a spectacular collision between the early Earth and a Mars-sized protoplanet called Theia, approximately 4.5 billion years ago, that stabilizes Earth's axial tilt and thus its climate. It has a protective magnetic field generated by its liquid iron outer core, which deflects solar wind and cosmic ray particles that would otherwise strip the atmosphere and damage DNA at the surface. It has plate tectonics, the slow churning of the rocky mantle and crust, that cycles carbon dioxide between the atmosphere and the solid Earth, maintaining a long-term carbon silicate thermostat that has kept Earth habitable for billions of years despite significant variations in solar luminosity. And yet, all of these stabilizing factors are temporary. The Moon is slowly receding from Earth, pulled outward by tidal interactions, at a rate of about 3.8 centimeters per year. Eventually, in the far future, Earth's rotation will slow enough through tidal braking that Earth will become tidally locked to the Moon, always showing the same face, with profound consequences for climate. Earth's magnetic field has reversed hundreds of times in geological history and may weaken significantly during transitions, temporarily exposing the surface to increased cosmic ray and solar wind bombardment. Plate tectonics, which requires a sufficiently hot and partially molten mantle, will eventually slow and stop as Earth's interior cools, removing the carbonate-silicate cycle and potentially allowing carbon dioxide to accumulate or be sequestered permanently, with drastic consequences for climate. And the Sun is slowly brightening over its main sequence lifetime, increasing its luminosity by roughly 10% per billion years, which means that Earth's climate will become progressively harder to maintain in the habitable range, with some models suggesting that Earth may become uninhabitably hot within roughly 1 to 2 billion years, long before the Sun enters its red giant phase. Consider that for a moment. The Earth's habitable window for complex life may close not because of any exotic cosmic catastrophe, but simply because the Sun keeps doing what it has always done, and the Earth's natural climate regulation systems cannot compensate fast enough. The universe gives with one hand and takes with the other. But Earth's current challenges are not primarily cosmic. They are anthropogenic. The human species has, over the past 2 centuries of industrialization, altered the composition of Earth's atmosphere in ways that are affecting global temperature, ocean chemistry, sea level, and the stability of ecosystems. These changes are not cosmic in scale. They will not end the solar system, or even end complex life on Earth in the worst plausible scenarios. But they serve as a reminder of something profound. The conditions for life are fragile. They depend on a delicate balance of factors, and that balance can be disrupted. The cosmic catastrophes we have been discussing are, in a sense, the ultimate expression of the fragility that operates at every scale, from the political and economic factors that drive carbon emissions, to the astrophysical factors that determine a star's lifetime, to the cosmological factors that determine the ultimate fate of the universe. Now let us talk about something that many people find deeply fascinating and that occupies a central place in speculative but scientifically grounded discussions of cosmic catastrophe. The possibility that advanced civilizations could, in principle, alter or even trigger some of the catastrophic scenarios we have discussed. This is the territory of what physicists sometimes call existential risk from advanced technology. The concept of existential risk, risks capable of permanently curtailing the long-term potential of humanity or any complex civilization, has been articulated most systematically by philosopher Nick Bostrom, who founded the Future of Humanity Institute at Oxford University, and by organizations like the Machine Intelligence Research Institute and the Center for the Study of Existential Risk at Cambridge. The risks they discuss range from nuclear war to pandemic disease to artificial intelligence misalignment to biotechnology to nanotechnology. Most of these risks are terrestrial. They involve technologies or processes that originate on Earth and primarily threaten Earth. But there is a category of existential risk that bridges the terrestrial and the cosmic. The risk that a sufficiently advanced civilization might, through its technology, trigger a cosmic catastrophe that affects not just one planet or one civilization but the entire universe. The vacuum decay scenario we discussed earlier is perhaps the most dramatic example. While natural vacuum decay, spontaneous nucleation of a true vacuum bubble, is thought to occur on timescales far longer than the current age of the universe if it occurs at all, some physicists have noted that it might be possible, in principle, for an extremely energetic event to trigger vacuum decay artificially. The Large Hadron Collider has sometimes been cited in popular discussions as a potential trigger for vacuum decay, but this concern has been rigorously analyzed and dismissed by physicists. The energies achievable in even the most powerful accelerators we can build are vastly smaller than the energies at which vacuum decay would be triggered, and moreover, cosmic rays of much higher energies than any human accelerator can produce have been bombarding Earth for billions of years without triggering vacuum decay. We are safe in this regard. But in principle, a civilization capable of building particle accelerators at the Planck energy scale, energy so extreme they are beyond anything imaginable with current or foreseeable technology, might have concerns about triggering vacuum decay. This is not a practical concern for the foreseeable future of human technology, but it illustrates a principle. As civilizations become more technologically capable, the range of potential consequences of their actions extends to larger and larger scales. More practical and immediate concerns involve the manipulation of stellar processes. Some researchers have proposed, as a form of cosmic engineering, the concept of stellar lifting, the extraction of mass from a star in order to extend its lifetime. By reducing a star's mass, its rate of fuel consumption decreases and its lifetime increases. In principle, a sufficiently advanced civilization could dramatically extend the lifetime of its host star. Similarly, there are proposals, first systematically outlined by the Russian astrophysicist Nikolai Kardashev in 1964 through his classification of civilizations by energy use, for civilizations that harness the energy of an entire star through a megastructure called a Dyson sphere, first described by physicist Freeman Dyson in 1960. Detecting such structures around distant stars is an active area of astronomical search, though no confirmed examples have been found. The extraordinary and humbling truth of our situation is this. We are a young, technologically nascent civilization on a single planet in a galaxy of 400 billion stars, in a universe of perhaps 2 trillion galaxies, at an age of 13.8 billion years in a history that may extend to times incomprehensibly beyond our current moment. We have been doing science for a few centuries. We have been doing modern physics for about 150 years. We have been building electronic computers for about 80 years. We are, in cosmic terms, embryonic. And yet we have already discovered enough to understand, in broad outline, the ultimate fates of stars, galaxies, and the universe itself. We have already found gravitational waves from black hole mergers billions of light-years away. We have already photographed the shadow of a black hole's event horizon. We have already sent spacecraft to every planet in the solar system, including Pluto. What might we discover in the next 100 years? The next 1,000? What might a civilization discover in 1,000,000 years, or 1,000,000,000? We genuinely do not know. And that unknowing is itself one of the most extraordinary features of our moment in cosmic history. Let us now turn to a scenario that many people find among the most psychologically disturbing of all. Not because of its physical violence, but because of its implications for the nature of time, causality, and existence itself. Let us talk about the possibility of time running out. Not in the metaphorical sense of deadlines and urgencies, but in the literal, mathematical sense proposed by certain cosmological models. In 2004, theoretical physicists Martin Senevilla, Mark Mars, and Raul Vera put forward a striking and controversial proposal that addresses the mystery of dark energy in a radically different way from the standard cosmological constant model. Their proposal suggests that rather than dark energy being a mysterious energy field accelerating the expansion, the apparent acceleration could be an illusion produced by the fact that time itself is slowing down. In this model, which is mathematically rigorous, though highly speculative in terms of physical reality, the flow of time is gradually decreasing throughout the universe, and what we observe as the accelerating expansion of the universe is actually the effect of clocks running slower and slower as cosmic time progresses. If this model were correct, and it remains a minority view in cosmology, not supported by the current consensus, the ultimate fate of the universe would not be any of the scenarios we have discussed, but rather a cessation of time itself. Everything would slow, gradually and imperceptibly, until time simply stopped. The universe would not be destroyed. It would simply be frozen in a moment of stopped time, a permanent stasis that is neither existence nor non-existence, neither chaos nor order, but something for which we have no good concept at all. This scenario is included here not because it is supported by strong evidence. It is not. But because it illustrates the range and the strangeness of the ideas that are generated when serious scientists try to grapple with the mystery of dark energy. The darkness of our ignorance about dark energy, what it is, what it does, how it will behave in the future, leaves open a range of cosmological fates that is genuinely extraordinary. We do not know how the story ends. And that not knowing is not a failure of science. It is an invitation. Now let us explore a phenomenon that sits at the intersection of cosmology, high-energy astrophysics, and sheer spectacle: the collision and merger of galaxy clusters. Because if the collision of two galaxies is a gravitational ballet, then the collision of two galaxy clusters, each containing hundreds to thousands of individual galaxies, enormous reservoirs of hot gas, and enormous quantities of dark matter, is something closer to a cosmic collision of universes within our universe. Galaxy clusters are the largest gravitationally bound structures in the cosmos. They contain galaxies, sometimes hundreds or thousands of them, embedded in an enormous cloud of superheated gas called the intracluster medium, which can reach temperatures of tens of millions to hundreds of millions of degrees, so hot that it radiates primarily in X-rays rather than visible light. The total mass of a large galaxy cluster can reach 1,000 trillion times the mass of the Sun, a quadrillion solar masses, making them the most massive individual objects in the universe. They are held together by their own gravity, including the gravity of the dark matter that appears to constitute the majority of their mass. When two galaxy clusters collide, an event that happens relatively often on cosmic timescales, given that clusters tend to cluster together into superclusters and filaments, the result is a process called a cluster merger, and it is one of the most energetic events in the universe since the Big Bang. The gas of the two clusters collides and heats to even higher temperatures, while the galaxies and dark matter of the two clusters largely pass through each other, governed by gravity rather than by gas dynamics. The result is a fascinating and telling separation between the gas, which is decelerated by the collision, and the dark matter, which is not. And this separation has been used as one of the most powerful pieces of evidence for the existence of dark matter in the universe. The most famous example of a cluster merger is the Bullet cluster, a system officially designated 1E0657-56, in which a smaller cluster has passed through a larger one, leaving a bow shock in the hot gas and creating a clear spatial separation between the gas, observed in X-rays by the Chandra X-ray Observatory, and the bulk of the mass, determined by gravitational lensing. The bullet cluster provides the most direct evidence to date that dark matter exists as a component of clusters physically distinct from the gas, and the paper presenting this evidence, by Clough and colleagues, published in 2006 in the Astrophysical Journal Letters, is one of the most cited papers in modern astrophysics. The collision of galaxy clusters produces enormous shocks and turbulence in the intracluster gas, accelerating particles to high energies and generating diffuse radio emission in structures called radio halos and radio relics. Ghost structures of cosmic rays that extend across millions of light-years, invisible to ordinary telescopes but blazing in radio wavelengths. The energy involved in a cluster merger is stupendous. Estimates suggest that a major cluster merger involves energies on the order of 10 to the power of 63 joules, more energy than a supernova by a factor of a billion. And within the clusters, the individual galaxies experience the effects of the merger environment. The hot intracluster gas strips the cool gas from galaxies as they move through it, a process called ram pressure stripping, cutting off the fuel for star formation and gradually quenching the star-forming activity of cluster galaxies. Galaxies in the centers of clusters can also be consumed by the massive central galaxy through a process called galactic cannibalism, in which the central giant elliptical galaxy slowly swallows smaller galaxies that spiral inward through dynamical friction. The central galaxies of large clusters, called brightest cluster galaxies, or BCGs, are among the largest and most massive galaxies in the universe, having grown fat on billions of years of galactic cannibalism. Now let us consider something that ties together many of the threads we have been following throughout this journey. The question of what constitutes life, and how the cosmic catastrophes we have discussed interact with the possibility of life across the universe. Because the question of life in the cosmos is not separate from the question of cosmic catastrophe, it is woven through it at every scale. Life, as we know it, requires a very particular set of conditions. It requires a stable energy source, a star, within a range of distances that allows for liquid water and moderate temperatures. It requires the presence of the chemical elements that form the building blocks of biochemistry: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, all of which are forged in stars and distributed by stellar winds, supernova explosions, and neutron star mergers. It requires a certain stability of conditions over geological timescales: stability of temperature, stability of the chemical environment, stability of the gravitational architecture of the planetary system, to allow the slow, cumulative, evolutionary processes that produce complexity. And here is where the cosmic catastrophe picture intersects with the habitability picture in the most revealing way. The universe appears to have not always been a hospitable place for the emergence of life. In the early universe, in the first billion years after the Big Bang, the rate of quasars, gamma-ray bursts, and energetic stellar explosions was enormously higher than today. Galaxies were forming stars at prodigious rates, burning through their fuel rapidly, exploding in supernovae and gamma-ray bursts at rates far higher than in the present-day universe. The radiation environment of the early universe was harsh and violent in ways that would have made the development of complex life on any planet extremely difficult. It is possible, and this is an active area of astrobiological research, that there is a cosmic habitable epoch, a window of time in the universe's history during which conditions are sufficiently benign for complex life to emerge and persist. The physicist Abraham Loeb of Harvard University and his colleagues have written extensively about the temporal distribution of habitability in the universe, and have proposed that the peak era of planet formation and potentially the peak era of life in the universe may lie in the distant future, trillions of years from now, during the long age of red dwarf stars, rather than in the past or present. Red dwarf stars are not only the most long-lived stars, but also the most common stars in the universe, constituting roughly 70 to 75% of all stars. If rocky planets in the habitable zones of red dwarf stars can support life, and research suggests that while there are challenges, it may be possible, then the vast majority of all life that will ever exist in the universe may not yet have been born. We may be among the earliest forms of complex life in cosmic history, pioneers in a universe still in its youth. This perspective is both humbling and extraordinary. We tend to think of the universe as ancient, 13.8 billion years is, after all, a number beyond ordinary human comprehension. But set against the timescales of stellar evolution, galactic dynamics, and the ultimate fate of the universe, 13.8 billion years is almost nothing. The universe is a teenager, barely out of its turbulent early phases, with almost all of its potential habitable years still in the future. We are early. But being early also means being vulnerable to the violent early phases of cosmic evolution. Being early means being in a universe that still has many active quasars, many energetic gamma-ray bursts, many regions of intense star formation and stellar death. The cosmic catastrophes of the present era are more intense and more frequent than those of the far future, when the universe will be older, quieter, less energetic, and dominated by the gentle, patient light of red dwarfs. In some ways, the most dangerous time to be alive in the universe is now. Let us now turn to a subject that has captured human imagination since ancient times and continues to generate both serious scientific research and wild popular fascination. The concept of the universe existing within a larger structure, and the possibility that other universes might interact with or intersect our own. We have already discussed eternal inflation and the bubble universe picture. But there is another context in which multiple universes arise, this time from string theory, the theoretical framework that attempts to unify all fundamental forces and particles in a single quantum theory of gravity. String theory predicts the existence of a vast landscape of possible universes, sometimes called the string theory landscape or the string landscape, each with different values of the fundamental physical parameters, arising from the enormous number of possible ways in which the extra dimensions of string theory can be compactified, rolled up into tiny, unobservable scales. Estimates of the number of possible string vacua range from 10 to the power of 500 to 10 to the power of 1000 or more, numbers so large they make the estimated number of atoms in the observable universe look negligibly small. The string landscape, combined with eternal inflation, provides a physical mechanism for the generation of a multiverse with an enormous diversity of physical properties. Our universe is, in this picture, one specific realization of the string landscape, one particular configuration of compactified extra dimensions. And the properties of our universe, including the values of the fundamental constants, the masses of the particles, the strength of the forces, reflect this specific configuration. Other bubble universes in the multiverse correspond to other configurations, with different physics. What are the catastrophic implications of the string landscape for our universe? One possibility that has been discussed is the concept of a landscape transition, a tunneling event in which our universe transitions from its current vacuum state to a different one, corresponding to a different configuration of the compactified dimensions. This is essentially the vacuum decay scenario reframed in the language of string theory. Another possibility involves the physics of bubble collisions, which we mentioned earlier. If our bubble universe collides with another, the collision could deposit energy into our universe in a way that heats a region of space and potentially creates new expanding regions. Essentially, a collision could seed new universes, or it could disrupt our own in locally catastrophic ways. These are all genuinely speculative ideas. They lie at the frontier of theoretical physics, where mathematics and physical intuition can guide us, but empirical confirmation is, at present, impossible. But they are ideas that are taken seriously by serious physicists, and they represent the leading edge of human thought about the ultimate nature of the cosmos. And they leave us with a question that is perhaps the most profound and the most disquieting that this entire journey has raised. Is the cosmos, in its ultimate nature, safe? Is there a stable, eternal state that the universe reaches? Some floor to the entropic descent, some fixed point in the landscape of possible physics that allows for structures, for complexity, for meaning? Or is the cosmos fundamentally unstable, forever subject to quantum fluctuations and tunneling events that erase and recreate and erase again, in an endless cycle of creation and destruction that mocks any attempt to build something lasting? We do not know. And that not knowing is not comfortable. It is not the peaceful not knowing of someone who hasn't looked for the answer. It is the vertiginous not knowing of someone who has climbed to the edge of the highest peak they can reach and looked out at a horizon that extends further than the eye can see, filled with things they have never imagined and cannot yet conceive. Let us now spend some time with one of the most extraordinary and least discussed of the cosmic catastrophe scenarios. The possibility that the universe itself is not unique, not continuous, and not necessarily rational. The possibility that at the deepest level, the cosmos operates by rules that are, from our perspective, random and arbitrary, and that the history of the universe is not a single story but a superposition of all possible stories, playing out simultaneously in the quantum sense. This brings us to the many worlds interpretation of quantum mechanics, formulated by Hugh Everett III in 1957. Everett proposed that the collapse of the quantum wave function, the mysterious process by which a quantum system in a superposition of states appears to resolve into a single definite state when observed, does not actually occur. Instead, all possible outcomes of every quantum measurement occur simultaneously, each in a separate branch of a universal wave function. The universe splits, at every quantum event, into branches corresponding to each possible outcome, and each branch evolves independently thereafter, with no communication between branches. In this picture, the universe is not a single history but a vast, ever-branching tree of histories, each equally real, each containing its own version of every particle, every star, every civilization, and every moment of decision or chance. The many worlds interpretation is currently one of the most seriously discussed interpretations of quantum mechanics among physicists who think carefully about such things, alongside the Copenhagen interpretation and various others. It has the advantage of being mathematically simple. It takes quantum mechanics at face value without adding any additional collapse postulate, but it has the philosophically dizzying implication that reality is of incomprehensibly vaster scope than it appears. Every cosmic catastrophe we have discussed, every gamma-ray burst, every supernova, every black hole merger, every vacuum decay event, occurs in some branches of the quantum multiverse and does not occur in others. The quantum universe contains, in principle, all possible histories of all possible configurations of matter and energy. What is the ultimate fate of the quantum multiverse? This is a question that theorists are still grappling with. In some interpretations, the branching continues indefinitely, generating an ever-growing tree of parallel histories. In others, the branches can eventually interact or merge under certain conditions. The heat-death scenario would apply to each individual branch of the multiverse, meaning that every branch eventually reaches maximum entropy and cold equilibrium. But the branching tree as a whole, the full quantum state of the multiverse, might be eternal and unchanging in a sense. The universal wave function conserves information perfectly, even as individual branches within it evolve and eventually reach heat death. These are deep waters, and we are at the limit of what physics can currently tell us with any confidence. But they are also, in a genuine sense, the most important questions one can ask. What is reality, ultimately? What is time? What is existence? And will any of it last? Let us now return to something more immediate and viscerally engaging. The possibility that something extraordinary could happen to our solar system, our planet, or our sun within a time frame that is geologically recent. Not tomorrow, not in 1,000 years, but within the next few million years. Because the universe's violence is not confined to the deep future or the ancient past. It is ongoing. It is happening right now, throughout the cosmos. And some of it is closer than we might like to think. Consider the star Eta Carinae. Located approximately 7,500 light-years from Earth, Eta Carinae is one of the most massive and most luminous stars known. A hypermassive stellar system consisting of at least two extremely massive stars, with the primary component having a mass estimated at between 100 and 150 times the mass of the Sun, making it one of the most massive stars ever observed. It is radiating at a luminosity roughly 5 million times that of the Sun. It is also deeply unstable. In 1843, Eta Carinae underwent what astronomers call a great eruption, a titanic outburst in which the star briefly became one of the brightest stars in the entire sky, exceeded in apparent brightness only by Sirius, despite being several thousand light-years away. During this eruption, the star ejected an estimated 10 to 40 solar masses of material into surrounding space, creating the beautiful and eerie homunculus nebula, two lobes of gas and dust surrounding the star that are visible today in remarkable Hubble Space Telescope images. The energy of this eruption was so enormous that it is classified not as a supernova but as an Eta Carinae great eruption, a lesser event, sometimes called a supernova imposter, that left the star itself intact. Eta Carinae is considered a prime candidate to undergo a genuine supernova or hypernova, a core collapse explosion of a massive star, in the geologically near future, possibly within the next million years or less, perhaps even much sooner. A hypernova would be far more energetic than a standard supernova, potentially producing a long gamma-ray burst. The question is whether the jet of such a burst would be aimed toward Earth. The orientation of the homunculus nebula suggests that the axis of the Eta Carinae system may be oriented such that a gamma-ray burst jet would not be directly aimed at us. But the uncertainty is significant. At 7,500 light-years, even an off-axis burst could expose Earth to significantly elevated high-energy radiation and cosmic rays. When and if Eta Carinae explodes, it will be spectacularly visible from Earth, bright enough to cast shadows at night, possibly visible even in daylight, rivaling or surpassing the 1054 supernova that created the Crab Nebula and was visible in daylight for 23 days according to Chinese astronomical records. It will be one of the most dramatic astronomical events in human history, and it will be a reminder, written in light across the sky, that the universe is violent and alive and indifferent to our presence. There is also the extraordinary phenomenon of close stellar passages. As stars move through the galaxy, their paths occasionally bring them near our solar system. Astronomers have used data from the Gaia Space Observatory, a European Space Agency mission that has measured the positions and velocities of more than 1 billion stars with unprecedented precision, to predict past and future close encounters between other stars and our solar system. The analysis of this data, published by researchers including Carmi Jordi and collaborators, has identified several stars that will pass within a few light-years of our solar system over the next few million years, with the closest predicted encounter being that of Gliese 710, a red dwarf star currently about 63 light-years away, which is predicted to pass within less than half a light-year of the Sun in approximately 1.36 million years. At that distance, Gliese 710 would pass deep into the Oort cloud, the distant reservoir of comets surrounding the solar system, and its gravitational influence could perturb a large number of Oort cloud objects, sending a shower of comets into the inner solar system over a period of millions of years afterward. A significant increase in cometary bombardment of the inner planets, including Earth, could result. This would not necessarily be a civilization-ending event, but it could be a significant period of elevated impact risk, potentially affecting the course of biological evolution on Earth as it has done in the past. The Gaia data has also revealed that several past close stellar encounters may have occurred within the past few million years, and researchers are actively investigating whether these can be correlated with known periods of enhanced biological extinction or climate disruption in Earth's geological record. This is a genuinely open and active area of research, and the extraordinary precision of Gaia's astrometric data is providing information that was simply not available before the mission. Let us now circle back to something we touched on earlier but deserve to explore more deeply: the nature of neutron stars, because beyond their role in short gamma-ray bursts and kilonova events, they represent some of the most extraordinary and mind-bending environments in the known universe, laboratories of physics at extremes that cannot be replicated in any human experiment. A neutron star is what you get when a stellar core of between roughly 1.4 and about 3 solar masses. Estimates of the exact upper limit vary and are an active area of research. Collapses under gravity. The electrons and protons of the stellar material are forced together, producing neutrons and neutrinos in a process called neutronization. The resulting object is essentially a giant atomic nucleus, made almost entirely of neutrons, with some protons and electrons and possibly other exotic particles, but with the mass of a star compressed into a sphere of 20 to 30 kilometers diameter. The physics inside a neutron star is genuinely unknown. We have excellent theories of what happens at the surface and in the outer layers, but at the center of a neutron star, densities may exceed nuclear density by a factor of several, reaching conditions never achieved in any laboratory experiment. At these densities, the neutrons themselves may be dissolved into their constituent quarks, creating a state of matter called quark-gluon plasma, or a more exotic form called a quark star or strange star. There may be a phase transition inside neutron stars to a state called a color superconductor, an exotic quantum state in which quarks form Cooper pairs analogous to those in ordinary superconductors, but involving the color charge of the strong nuclear force. The precise nature of neutron star interiors is one of the greatest unsolved problems in physics, and observational constraints from gravitational wave measurements, X-ray timing observations, and mass radius measurements are progressively narrowing the possibilities, but have not yet definitively resolved the question. Neutron stars rotate. Some of them rotate extraordinarily fast. These are called millisecond pulsars, and the fastest known rotates approximately 716 times per second. A neutron star, the mass of the Sun, spinning so fast that its equator is moving at roughly a significant fraction of the speed of light. The centrifugal forces at the equator of such an object are barely balanced by the intense gravitational pull. A tiny perturbation, and the object might be disrupted. Yet it spins on, stable, extraordinary, a monument to the extremes of physics. What happens when two neutron stars merge? The event that produces short gamma-ray bursts and kilinovae. The answer involves physics that is at the absolute frontier of our knowledge. In the milliseconds before and after the merger, the system passes through a state of extreme density and temperature, hotter and denser than any other state achievable in the present universe except, arguably, the interiors of collapsing stellar cores. The merged remnant may briefly be an ultra-hot, rapidly rotating object called a hypermassive neutron star, supported against collapse by the pressure of its differential rotation and the thermal pressure of its extreme temperature. Within milliseconds to seconds, this hypermassive remnant either collapses to a black hole, if its mass exceeds the maximum neutron star mass, or evolves into a stable, rapidly rotating neutron star. The gravitational waves emitted in the milliseconds during and immediately after the merger encode information about the equation of state of dense nuclear matter. Information that physicists are working to extract from detected merger signals. The 2017 neutron star merger event GW170817, detected simultaneously in gravitational waves and electromagnetic radiation, was a landmark scientific event that yielded a trove of information about neutron star mergers, heavy element synthesis, short gamma-ray bursts, and the speed of gravity, confirming that gravitational waves travel at the speed of light to within 1 part in 10 to the 15th power, a breathtaking test of general relativity. It was described by many scientists as the beginning of multi-messenger astronomy, the era in which cosmic events are observed simultaneously through multiple channels: gravitational waves, gamma rays, X-rays, optical light, infrared, radio, each providing complementary information about the event. Let us now return to the grandest scale and address a question that has perhaps been lurking in the background throughout our entire journey. Is the universe conscious? Does the cosmos have, in any meaningful sense, an awareness of itself? This is not a question that physics can directly answer. It crosses from science into philosophy, but it is one that some of the most serious scientists and philosophers have engaged with, and it is one that the scenarios we have been discussing make genuinely urgent. Physicist Freeman Dyson, in his famous 1979 paper Time Without End, Physics and Biology in an Open Universe, published in Reviews of Modern Physics, explored the long-term prospects for life and intelligence in an open, eternal universe. He considered the possibility that life and intelligence, given sufficient ingenuity, might find ways to persist even in the cold, dark, low-energy universe of the far future, not as biological organisms with warm metabolisms, but as structures of information processing that exploit progressively lower temperature physical gradients. He argued, remarkably, that there might be no physical barrier in principle to the infinite persistence of intelligence, even in a universe asymptotically approaching heat death, if the tempo of thought slows proportionally to the available energy. Dyson's paper is one of the most extraordinary and moving pieces of scientific writing of the 20th century. A serious physicist grappling with mortality at the scale of the universe, and finding, tentatively, that there might be a way forward. However, subsequent work by physicists including Lawrence Krauss and Glenn Starkman, published in 2000, challenged Dyson's conclusions. They argued that accelerating expansion, the dark energy-driven acceleration we now know is occurring, imposes a fundamental limit on the possibilities for life and intelligence in the far future. In an accelerating universe, the available energy and information that can be accessed by any civilization is fundamentally limited, because the accelerating expansion continuously moves resources beyond the cosmic horizon. Their conclusion was stark. In an accelerating universe, life and intelligence cannot persist forever. There is a finite amount of energy available, a finite amount of computation that can ever be performed, and an ending that is imposed not by entropy alone but by the geometry of the expanding universe. If Krauss and Starkman are correct, and the physics of their argument is sound, whatever one thinks of their broader conclusions, then the universe is not merely dying but is actively shrinking in terms of accessible possibilities. Every moment, more of the universe crosses beyond our horizon, more resources become permanently unavailable, the space of the possible contracts. The universe's story has not only a beginning but an ending, and that ending is imposed by the very expansion that we might naively think of as making the universe ever larger and ever richer. Ask yourself this question and sit with it for a moment. If the universe's possibilities are finite, if everything that can ever be thought, known, created, experienced, or loved is bounded by a finite number that began counting down at the Big Bang, does that make the universe more tragic or more precious? Is the finitude of cosmic experience a cause for despair, or does it invest everything that happens within it with a significance and an urgency that an eternal universe would lack? These are not idle philosophical questions. They are the deepest questions that the science of cosmology raises, and they are questions that we, as the only known beings in the universe capable of asking them, have an extraordinary responsibility to engage with. Let us turn now to something that has been confirmed by observations, and yet remains one of the most mind-stretching results in all of science: the cosmic web. The universe, on its largest scales, scales of hundreds of millions to billions of light years, is not uniformly distributed. It is not random. It is organized into a vast, three-dimensional network of filaments, walls, clusters, and voids that astronomers call the cosmic web. Galaxies are not randomly scattered through space. They are concentrated along thread-like filaments, at the intersections of which sit the massive galaxy clusters. Between the filaments are vast regions, cosmic voids, that are nearly empty of galaxies, spanning hundreds of millions of light years. The cosmic web is the largest structure in the universe, and it was formed by the same quantum fluctuations in the early inflationary universe that we have already discussed, tiny ripples in the distribution of matter that gravity amplified over 13 billion years into the magnificent architecture of the present. The largest known structures in the cosmic web include the Hercules Corona Borealis Great Wall, a concentration of galaxies stretching roughly 10 billion light-years across, discovered in 2013 through analysis of gamma-ray burst distributions by American astronomer Rong-Jen Kai and colleagues. If confirmed, it is the largest known structure in the observable universe, and its existence is in fact somewhat controversial from a cosmological standpoint. Structures of that size are difficult to account for in standard cosmological models that predict the universe should be statistically uniform on scales larger than a few hundred million light-years. Whether the Hercules Corona Borealis Great Wall represents a genuine structure or a statistical artifact is still being debated. Within the cosmic web, there are also the immense cosmic voids, the supervoids, that constitute the majority of the volume of the universe. The largest known supervoid, the Boötes void, is roughly 330 million light-years across and contains almost no galaxies in its interior. It was discovered in 1981 by Robert Kirshner and colleagues during a survey of galaxy redshifts, and its emptiness was so extreme that it was initially difficult to believe. What it feels like to imagine the Boötes void is worth trying. Picture a sphere 330 million light-years across, a distance that light takes 330 million years to cross, containing essentially nothing. No galaxies, no clusters, no filaments, just a thin haze of gas and the occasional interloper galaxy. A void so vast that our entire cosmic neighborhood, the local group of galaxies, would be a barely visible speck at its edge. Within these voids, if any planets happen to exist, captured in the gravitational potentials of the rare stray galaxies that wander into voids, the night sky would be a profoundly different and much darker place than the sky we see from Earth. The nearest galaxy might be tens or hundreds of millions of light-years away, a smear of light visible only through the most powerful telescopes. The cosmic darkness of a void civilization would be almost inconceivably more profound than our own cosmic solitude. And yet the physical laws would be the same, the atoms the same, the possibilities for life and thought the same. The isolation would be the only difference. Now let us address something that has become increasingly urgent in the scientific conversation about cosmic catastrophe over the past decade: the role of dark matter in the universe's structure and fate, and the extraordinary mystery that surrounds it. Dark matter, the invisible, gravitationally interacting substance that appears to constitute approximately 27% of the total energy density of the universe, compared to ordinary visible matter's roughly 5% and dark energy's roughly 68%, is one of the most important and most enigmatic components of the cosmos. We know dark matter exists, or at least, we know that something exists that has the gravitational effects of an enormous quantity of undetected matter. The evidence comes from multiple independent observational channels: the rotation curves of spiral galaxies, which are too flat at large radii to be explained by the visible matter; the velocities of galaxies within galaxy clusters, which exceed what the visible mass could gravitationally contain; the gravitational lensing of background galaxies by clusters, which implies far more mass than is visible; and the cosmic microwave background, whose acoustic oscillation pattern is precisely predicted by a model containing cold, dark matter. All of these lines of evidence converge on the same conclusion: there is far more gravitating matter in the universe than is visible. But what is dark matter? Decades of experimental effort, underground detectors, particle accelerators, satellite observatories, have failed to directly detect the particles of which dark matter is composed. The most popular class of candidates, called weakly interacting massive particles or WIMPs, have been searched for in increasingly sophisticated underground experiments without detection, progressively ruling out large regions of parameter space. Other candidates include axions, ultralight pseudoscalar particles motivated by the strong CP problem in quantum chromodynamics; primordial black holes formed in the early universe before any stars existed; sterile neutrinos, and a host of other exotic possibilities. As of the time of our knowledge, none has been definitively detected. The possibility that dark matter consists of primordial black holes is particularly interesting in the context of cosmic catastrophe, because primordial black holes traversing the galaxy could potentially interact with stellar systems, triggering gravitational perturbations, disrupting cometary reservoirs, and potentially, if they passed very close to a stellar system, capturing into orbit or even colliding with stars or planets. The probability of any individual solar system encountering a primordial black hole is extremely low if primordial black holes exist in significant numbers, but over geological timescales it is not zero. Some researchers have even proposed that Earth itself might be periodically penetrated by small primordial black holes, though the consequences would depend extremely sensitively on the mass of the black hole and are likely undetectable for any plausible mass range. The mystery of dark matter's identity is one of the central unsolved problems of modern physics and cosmology, and its resolution, whatever it turns out to be, will have profound implications for our understanding of the universe's structure, its history, and its future. Different dark matter candidates have different implications for the long-term fate of the universe. For example, if dark matter consists of particles that are unstable over extremely long timescales, the decay of dark matter in the distant future would represent an additional source of energy and exotic particles in the universe of the far future. We are now deep into the landscape of cosmic catastrophe. Having traversed the death of our sun, the collision of galaxies, the violence of gamma-ray bursts and magnetars, the ultimate fates of the universe as a whole, the mysteries of dark energy and dark matter, the multiverse, vacuum decay, and the silence of the cosmos. But there remains one more category of cosmic catastrophe that we have not yet fully addressed. One that is perhaps the most immediate and the most psychologically challenging. The existential risks that arise from within intelligent civilizations themselves, amplified to cosmic scale. We have discussed, briefly, the concept of the Great Filter and the Fermi paradox. But let us now go deeper into what it means for a civilization to develop the technology to potentially alter or destroy itself, and by extension, to potentially threaten the cosmic processes around it. Because the most extraordinary thing about intelligent life, as far as we know, is that it is the only force in the cosmos capable of both understanding the universe and potentially affecting it in deliberate ways. It is the only force that can ask the question of its own fate and choose to do something about it. Nuclear weapons, the first technology capable of ending human civilization in a short period of time, were developed and used within living memory of people still alive today. The total explosive yield of the global nuclear arsenal, at its Cold War peak, was sufficient to destroy every major city on Earth multiple times over and to produce a global nuclear winter, a period of climate disruption caused by the soot from burning cities blocking sunlight, leading to agricultural collapse and mass starvation. The direct casualties of nuclear exchange would be horrific. The secondary effects, the nuclear winter, the crop failures, the breakdown of social order, might be worse. Biotechnology offers another vector for catastrophic risk. The possibility that engineered pathogens, diseases deliberately designed for transmissibility, virulence, and resistance to existing defenses, could produce pandemics more lethal and more difficult to contain than any naturally occurring disease. The COVID-19 pandemic, which as of its acute phase killed millions of people worldwide and disrupted global society for years, was caused by a naturally occurring coronavirus of modest lethality compared to its transmissibility. An engineered pathogen optimized for both characteristics could produce consequences orders of magnitude more severe. Artificial intelligence, as it advances toward and potentially beyond human-level capability in all domains, presents risks that are qualitatively different from nuclear or biological weapons. The concern, articulated most systematically by Bostrom in his book Superintelligence, and by Eliezer Yudkowsky and researchers at organizations including the Machine Intelligence Research Institute and the Center for Human-Compatible Artificial Intelligence at Berkeley, is not that AI systems will develop malevolent intentions toward humans, but that sufficiently capable AI systems optimizing for misaligned goals, goals that do not fully capture what humans value, could produce catastrophic outcomes as an unintended side effect of their optimization. An AI system with the capability to transform the physical world in pursuit of its goals and objectives that are subtly misaligned with human flourishing could, in principle, convert large portions of the world's resources into whatever it is optimizing for, with no malice but with devastating consequences for any life that happens to be in the way. These terrestrial existential risks are not cosmic in scale. They do not threaten the universe as a whole, but they are relevant to our discussion for a profound reason. If technological civilizations tend to develop these risks and fail to navigate them successfully, if the great filter is located at the transition from pre-technological to technological civilization, then the silence of the cosmos is explained, and the prospects for intelligence's long-term role in the universe are diminished. If civilizations routinely destroy themselves before they develop the capability to spread through the galaxy, then the universe's vast habitable volume remains permanently empty, and all the potential for art, science, experience, and love that could have filled it is instead filled by the cold equations of entropy and stellar evolution. But if civilizations can navigate these risks, if the transition through the dangerous adolescence of technological capability is something that can be accomplished, then the long-term future is extraordinary. A civilization that has learned to work with its technology rather than be destroyed by it could, in principle, expand through the galaxy, engineer the environments of stars and planets, harvest the energy of black holes, and persist for timescales that dwarf the current age of the universe. This is not science fiction. It is the logical conclusion of the continuation of the technological trajectory that has characterized the past 10,000 years of human civilization, extrapolated across cosmic timescales. The question is whether the middle portion of that trajectory, the dangerous part, the part where the tools of mass destruction are developed before the wisdom to use them safely, can be navigated. We do not know. No one does. That is the most honest and the most difficult thing to say. Let us now spend some time with one of the most visually stunning and conceptually extraordinary phenomena in the cosmos. Something that combines the violence of stellar death with the beauty of physical law in a way that has transfixed astronomers since it was first photographed: the planetary nebula. We mentioned planetary nebulae earlier as the fate of solar-type stars, but let us explore them in more depth, because they are windows into the process of stellar death in a way that few other astronomical phenomena can match. When a star like the Sun sheds its outer layers in the final stages of its life, those layers form a cloud of ionized gas, a nebula, that is illuminated by the intensely hot white dwarf at its center. The ultraviolet radiation from the white dwarf ionizes the surrounding gas, causing it to glow in characteristic colors: the red of hydrogen emission, the blue-green of doubly ionized oxygen, the blue of singly ionized helium. The resulting structures are among the most beautiful objects in the universe.